Today I'm talking about different solution concepts for games and game theory. And first we need to try to understand what is a solution concept for a game. So when we say game in economics, we basically mean a strategic interaction of two or more people. So for instance, a goalkeeper and a shooter at a penalty in soccer. Or it could also be people who are doing a contract with each other. For instance, to reduce emissions, like multiple countries interacting with each other. Or it could also be companies setting prices for their products and interacting with the other companies who operate in the same market, who, for instance, also sell cell phones. And our solution concept is our way of trying to understand if we set the rules of the game in a specific way. For instance, if we set an emission price of €5 per ton CO2, how are the players going to react? Are they going to reduce their carbon emissions by how much, or are they going to ignore this? And what actually happens if we, put our emission price at €50 per ton? So this is what a solution concept is going to try to tell us. How are the people going to react if rules are set in a certain way? And in economics, we need to choose the solution concept that best fits the setting of our game. And I'm going to present to you 3 solution concepts which all have different assumptions on the setting of the game. The first is the one with the least assumptions. It's the called dominant strategy solution concept. That means that every player plays the strategy that is always best for him. And here is a game. So we have 2 players, they're called B and S, and they can both play action 1 or 2, right? And let's try to focus on player B first. So player B will always want to play action 2. Why? Well, look at the situation. If he plays action 1 in this first case, he's going to get a payoff of 5, but with action 2, he's going to get a payoff of 6. If player S plays action 2, well, player 1 is going to get a 0 if he plays 1 and a 1 if he plays 2. So in other words, no matter what player S does, player B will always play alternative 2. This is a dominant strategy for him. So let's look at player 2. Well, player 2 will always want, player S will always want to play 2, right? Why? Because in every situation, it is giving him a higher payoff than playing strategy 1, right? Here, if player B plays 1, player S gets the payoff of 5 if he plays 1 and the payoff of 6 if he plays 2. And the second situation, player S gets a payoff of 0 if he plays 1 and a payoff of 1 if he plays 2. So this gives us an equilibrium in dominant strategies. If the rules of the game are set in this way, both players will play action 2. In other words, they will both generate a payoff of 1, right? So if we have a real-life situation that we can model by such payoffs, and we see that player B and player S have a dominant strategy, in other words, a strategy that always gives them a better payoff no matter what the others do, we can actually find a solution or find a prediction for what players will do. And this, of course, helps us to evaluate if our idea of setting the rules differently, of setting our carbon price on 15 or 20, is actually good or bad idea. However, in most situations, there is not a clear dominant strategy. And that is where we use rationalizability, our second solution concept. But for this, we need another assumption. We need the assumption that players think about the strategy of the other player, which is an assumption, right? We didn't need this with dominant strategies because our players had a dominant strategy no matter what the others do. And now we add this assumption that players actually think about what the others are doing. And what we call a rationalizable strategy is a strategy that survives the elimination of strictly dominated strategies. That might seem a bit complicated, but I'll just show it to you in an example and it will become very clear. So once again, we have 2 players, and player 2 can play left, center, right, and player 1 can play top, middle, down. So let's focus on player 1 first. So if player 2 plays left, player 1 will want to play middle. If player 2 plays center, player 1 will want to play middle. And if player 2 plays right, player 1 will want to play top, because they get the highest payoffs in those instances. If that was a bit too fast, just stop the video and think about it yourself. So what do we see? We see that player 1 will never play down. And what is our assumption? Our assumption is that player 2 thinks about the strategy of player 1. So player 2 will know that the strategy down will never be played by player 1. So we can actually eliminate this row because it will never be played. All right, so we have found a more easy game. Let's try to look at player 2 now. So if player 1 plays top, player 2 will want to play center. If player 1 plays middle, player 2 will want to play left. In other words, player 2 will never play right because it's just never a good option for him. And once again, we have the assumption that also player 1 thinks about the thinking process and strategy process of player 2, so he knows that player 2 will never play right. So we're left with an even simpler game. Let's look at this simpler game in more detail. What is player 1 now going to do? Well, if player 2 plays left, player 1 will play middle. If player 2 plays center, player 1 will also play middle. Once again, we can eliminate the top strategy. It will never be played by player 1. However, if player 1 plays middle, we know that player 1 will want to play left. So we have found our equilibrium. So in other words, in this game, with this payoff and with the made assumption, we find that the players will act left and middle. So this is our rationalizability, right? However, it is not always the case that we can eliminate strategies because they're strictly dominated. And in this case, we introduce another solution concept, the Nash Equilibrium. And the Nash Equilibrium needs another assumption. And this assumption is that the player actually knows about the response of the others, knows about others' responses, which is once again a stronger assumption about others', let's say, actions. Because with rationalizability, we only needed that players think about the strategy of others. Now we have a stronger assumption. Player knows what the others are doing, right? This might be, for instance, a very good approximation in traffic, right? In Germany, everybody drives on the right side of the road, for instance, right? And this would be common knowledge. So this could be an instance where the Nash Equilibrium concept actually is a good idea. And what is the Nash Equilibrium concept? Everybody best responds, or an equivalent definition would be that no one has the incentive to deviate. I'm just going to show it to you in this game. So let's think about player 1 again, right? And let's think about if player 2 plays A, right? So we're in this bucket. Well, player 1 will want to play B because he has a higher payoff, right? 3 is greater than 2. Okay, let's think about the second action. What happens when player 2 plays B? Well, player 1 will want to play A because 2 is greater than 1. Okay? Let's think about player 2. What if player 1 plays A? Well, player 1 wants to play B because 2 is greater than 1, his payoff. And last thing, if player 1 plays B, player 2 will want to play A because 1 is larger than 0. Okay, so what have we found? We have found two Nash equilibria, AB and BA, right? So let's say as player 2, I know that player 1 is playing A. What do I mean with I don't have the incentive to deviate? Well, as player 2, I don't want to play action A now, right? Because I only get a payoff of 1 in action A, and I actually get a payoff of 2 in action B. So player 2 has no incentive to deviate from this situation. Let's look at player 1. So if I know that player 2 plays B, then I will want to play A, because 2 is a higher pair than 1. So this is an equilibrium. So if we set the strategy, if we set a game and we assume that everybody knows what the other's actions are, then AB is an outcome that we can expect. However, it can also happen, and you can verify this yourself, that BA is an outcome that happens, because this also satisfies the properties everybody best responds or no one deviates. And this is a problem that you see with the Nash equilibrium. With the Nash equilibrium, you not always get a unique answer, right? So you set the rules of a game, you're trying to think what the players are doing, and then you get two answers, right? And depending on your application, this might actually be bad, right? But in many cases, this is a good starting point, because if you find Nash equilibria, well, they're reasonable outcomes of the game, then you can think about, well, which Nash equilibrium is more likely in my setting. Yeah. So let's wrap up this video. So what have we thought about? We have thought about solution concepts for static games. So we're trying to predict how people are going to react in certain situations, right? And depending on what we can assume in a situation, maybe we can assume that everybody knows the other player's actions. For instance, in traffic, everybody knows that the other people will drive on the right side, so it will be very smart for me to also drive on the right side if I don't want to have a crash, right? Maybe I can assume that players are able to think about the strategy of the others. Then I can use the solution concept of rationalizability. And the weakest solution concept is the dominant strategy concept, where I just think about my own strategies, right? So with these three solution concepts, our assumptions grow stronger from solution concept 1, 2, 3. Our assumptions get stronger. This is it for the video. If you have questions, leave it in the comment section below.